Well, good morning, everybody. As I said, my name is James Monroe, and so I'm here on behalf of 2I2C, and we run a managed Jupyter Hub on behalf of the M2LINES community. And I think what I'm going to end up doing is doing a fair amount of screen sharing to talk about cloud computing with Jupyter Hub in the context of the M2LINES community. This is one of those interactive kind of things. So once I've done a little bit of introduction, you're more than welcome to spin up your own Jupyter Hub instance. If you have used Jupyter Hub before, you do know it takes a few minutes to get started. So if you know how to do that and you can launch right into it and create a huge instance on the hub, that'd be fantastic. And if you don't know what that means, wait a few minutes and we'll get through it. As I said, I'm employed with 2I2C in the role of a relatively new product and community lead. And so my position is to sit at the interface between the engineering team at 2I2C, who actually deploy the cloud infrastructure and keep things up and running, and the science users, whether or not that be education or research. I'm just coming from an academic position. I've actually just gotten a leave from a university in Eastern Canada, where I worked as a physical oceanographer, looking at big data, ocean, supervising a graduate student on machine learning for exoplanets. So I know a little bit about this space from a science and research point of view, but I'm here primarily as an intermediary between the two groups. And my hope and my goal is to ensure that you're able to utilize the Jupyter Hub that 2I2C has set up, and it actually adds value to your research work. So here are my goals for today. I've been told we have about a 2-hour break. If you have to break off and leave for something, that's no problem. I will attempt to keep a chat window open. So if I'm missing something or my audio drops off, please fire something in the chat, and that will tell me that I need to pay attention or do something. But I said, if you're able to sort of put this screen share on one side of your screen and another web browser on another, that's ideal. If you just like to sit back, relax, have a cup of coffee and watch, that's also, of course, your choice. So here's my goals for today. I'd like to do a little bit of a guided tour of what this Jupyter Hub interface or infrastructure actually is that's been spun up. Talking around a little bit of discussion on Git and GitHub and how that could be useful in collaborating in research when you're talking about a community like M2LINES. A lot of the focus will be on data, getting data into the hub, some opportunities and some challenges with data. And on the background here, though I'm not going to pretend that I can teach very many people in this group much about it, is the conversation around what possibilities might exist for doing machine learning with various packages on this infrastructure. So here's my assumption. And I said we have a fairly big group, about 30 people, but M2LINES is a large team. I'm going to make the assumption, and if I'm wrong, I apologize, that this group has previous experience with Python, is used to using Jupyter notebooks as a way of communicating backwards and back and forth. You're all studying, working in science, advancing machine learning. So you might be familiar with scikit-learn or PyTorch or some other framework. And generally, everybody in this conversation is really interested in advancing Earth systems modeling, right? That's sort of how these things all come together. So that's the context in which I'm pitching this. If those topics are like, actually, I know nothing about Python, let me know after it, and I will come up with or point you to some resources to fill in that gap. Okay, so I guess the first thing to talk about is what do we mean by a Jupyter Hub? So I want to talk about the difference between a Jupyter Notebook and a Jupyter Hub. So Jupyter Notebook, so anytime you see that extension, IPYNB, it's an example of what's called a computational notebook. So this thing I'm looking at right now, this is being loaded up in the Jupyter Lab interface, and I'm looking at a Jupyter Notebook. So if you go in here on the file browser, IPYNB, that's what this thing is. Internally, it's a big JSON file, and it allows you to have within it text, pictures, and then we'll get down to it, code and an output all mixed up together. So it's an implementation of a literate programming model, and it's really ushering in a new wave of interactive collaborative science. Now, Jupyter Notebooks aren't the only framework out there. I've heard some really interesting about Cordo and what Posit, who used to be RStudio, are doing in the R ecosystem. But the whole idea of trying to make our publications, our papers, not static documents, but living things that can be interactively played with and explored is opening up a real tool for collaborative science. And so there's a relatively recent op-ed piece in EOS by Chris Erdman and co-authors, identifying that these collaborative workbooks, these collaborative notebooks, are letting us share our workflows and data analysis with each other. They are infrastructure that various research compute servicing units are going, okay, we need to bring that in because our users are demanding it. We want this way of working with this data. And so these notebooks are becoming more ubiquitous in research. And what they allow is this fusing together of the data and the visualization and the code all in one cohesive document. So when I think about a Jupyter notebook as an example of a computational notebook, it's this item, it's this thing that combines the text, the code, the output, the plots into a cohesive whole. Now, Jupyter Notebooks is actually only one part of a whole ecosystem of products that's all under the Jupyter project. So if you go on that link and you go to Jupyter project, you'll find that it's an open source project trying to innovate in this space. Jupyter as a thing came out of the IPython interactive Python interpreter. So Fernando Perez and his work initially turned out that it's useful for more than just Python. So Jupyter, right? The JU is Julia, the PY is Python, and the R of Jupyter is R, but it supports even more languages. I've seen support for Jupyter that includes Fortran as an interactive Fortran, which is a little bit of a mind meld going, what do you mean Fortran can be interactive? But what's going on is on the back end, a little code snippet can get compiled on the fly and you can see the output of it. So it's a way of interactively working with your code. It doesn't preclude use of other tools, whether or not there's be IDEs, something like a VS Code or another framework. It's just another tool we can use for building up our code. One of the other projects within the Jupyter ecosystem is called Jupyter Hub. So Jupyter Hub is a piece of software that allows multi-user versions of Jupyter servers to work together. And it's typically used by companies, by classrooms, or in this case, by a research group. And so what we are looking at right here, what we're staring at is actually just an instance logged in through a web browser of something called Jupyter Hub. So that's the software you're actually talking to when you go to a website and you log in. And what Jupyter Hub does is it spins up for you a Jupyter server instance that's living in the cloud on a server that you can have access to. So you have all the power of whatever server you're connected to with a very nice fast internet connection because it's sitting on the cloud and ideally proximate to where your data is. So we start. Where is this hub thing? So I'm sure you all know this, but just in case. So when we're talking about the M2LINE hub, we're talking about this URL, right? So m2lines.2i2c.cloud. So I'm from 2i2c. 2i2c is the group of cloud engineers, site reliability engineers, and open infrastructure mavens who run this thing. They build together the expertise you need to keep a larger deployment of these things up and running. My own background, I said I'm a researcher, but I've also spun these things up in the past. Spinning up the infrastructure, getting an account on Google Compute Cloud or Amazon Web Services, spinning up a virtual machine, installing Jupyter, actually not that bad. Many people in this group, I'm sure, are totally capable of getting it going. The hard part is the support and maintenance of it. Keeping a system up and running at scale, whether or not that's security issues or updates or just changes to the cloud infrastructure, that's a skill set. That's what a site reliability engineer or a cloud engineer does. 2i2c has those people, so you can focus on your science and not have to be weighted down by that cloud engineering. Now, saying that, one of the things we practice within 2i2c is open infrastructure and the right to replicate. So what that means is, if you so chose that at one point in the future, either M2LINES as a group or someone within this group goes to another institution, wants to spin up their own independent Jupyter Hub instance, and they want it to be exactly like this is set up, all of the infrastructure as code we use is publicly available, right? So here's a link, so I'll just like show it to you. So in a GitHub repository, this is public, we have the cluster for M2LINES, and these are the configuration files, right? So anyone can go and see what this is made up of, right? So the way that this thing is deployed, there are a bunch of YAML files, and they configure things. They configure things like it's on Google as opposed to Amazon or Azure, what the actual logo looks like and that low line things, who's authenticated to it. So we use GitHub to authenticate users onto the hub, and then a few details about what kind of images or systems or nodes that you could spin up all the way through there. So it's transparent, you can see it. The only thing that of course is not directly on these are the secrets, the codes, the tokens. They're there, right? So there are all the secrets to connect to this thing, but they're all encrypted. So there's a few security things, we don't make that completely public, but all of the structure is there. So if you cared or were interested, you could find out how the black box works, but there's no requirement. I don't know about you, but as a technical person, someone who's on the interface of high performance computing and earth sciences, I like to know the technical details of what am I actually logging into? What am I working with, right? When you buy a desktop or a laptop, some people care about like, well, what kind of operating system you're running? What version of a processor is in there? How much RAM do you got, right? We care about these things. Maybe not everybody, but some does. So for this particular Jupyter Hub, it's running on Google Cloud Platform. It's physically in Council Bluffs, Iowa. That's where the US Central One data center is. We're talking about a 115,000 square foot facility. Interestingly enough, it's almost carbon-free energy all the way through. So they've obviously got access to some sort of renewable energy, which is pretty cool. And what makes it up are a bunch of standard general purpose machines on a whole several generations of different Intel CPU architectures. Each one of these machines probably is actually multiple cores inside on a main board, and it can support up to like 96 virtual CPUs. And these boards are pretty maxed out in memory, right? So some of them have up to 624 gigs of RAM. So in terms of a snapshot of what is this thing, right? So you may have had a tour of an HPC center or some data center, but this is a snapshot of the inside of the Council Bluffs, Iowa data center of Google. So right now I am logged in and showing you stuff running on one of those blinking lights in one of those racks, in one of those boxes somewhere in that data center, and that's what we're connected to. Of course, the advantage here of doing cloud computing is the co-located compute and this amazing network backbone, right? So this is Google, right? This is the fastest way of moving things around the commercial net, and so you can get data. But your data that you're accessing might very well live on another one of those racks somewhere else in this room, and so the interconnect between them is really, really fast without having to have that locally within institution. M2LINES is multi-institutional, so using something like the public cloud is a great way of accessing it. The other piece of technology here is some of those nodes actually have got some GPUs. I think we set up things with NVIDIA Tesla K80, so just under 5,000 CUDA cores on those things, which we have access to as well. Okay, so let's begin. Let's get into it. Thanks for the chat. If you're here from the Leap group, there's an equivalent infrastructure set up at leap.2i2c.cloud. Though if you're following along at home, I haven't set up anything for the Leap folk because I didn't know you would be here. But I'm sure a lot of it will be tractable, even if it won't work if you're not on the M2LINES shared cluster. Okay, number one, let's take a look and see whether or not we can get this going. Now, again, this is tailored for the M2LINES community, so I assume you have an account on this. If you'd like to follow along on a different server, some of this will work, maybe not all of it, but some of it might work. We'll see. So I'm going to get you to log into that web browser. And the way that this works is you get a little splash page, you click login to continue. The actual authentication, what gives you permission to log in is you are a member of a GitHub organization called M2LINES. And so what that tells me is everybody who's using the server should have a GitHub credentials. And I think for us, let's try and just use the huge instance to get this going and start it. Now, when you go into this service, it takes, or you might be familiar, it takes a moment to get started. So what it's doing behind the scenes, and this is the cloud engineering stuff, not that you need to know about it necessarily, but it's nice to know what's going on, right? You hit go, and you don't necessarily get a Jupyter server instantly. You get it pretty quick, but you don't get it instantly. So what's going on? What's going on is this technology called Kubernetes. Kubernetes is container orchestration software. It is figuring out how to take the software we're looking at, Jupyter Lab or Jupyter Server, and get it deployed onto one of these machines. Now, there's a subtlety between containers and virtual machines. If you're familiar with, I can spin up a virtual machine on a cloud infrastructure, that's sort of like a full operating system with its own base image, and you install software on it. Strictly speaking, we're dealing with containers. Containers are sort of a lightweight virtual machine. They spin up a little bit faster than a virtual machine. And what Kubernetes is doing is allocating these containers or these operating system-like images onto the resources that form part of a cluster. Now, the clusters are auto-scaling. So when you come on, if you're the first person to join this cluster, what will happen is the infrastructure will go off and say, look, I've only spun up like 2 or 3 physical nodes, physical computers. If you have more users, I need to allocate or provision more systems. So that will happen, and that takes a moment. And then the software, the actual container image that has all the libraries and resources. And for M2LINES, the default is actually just the Pangeo notebook gets downloaded. And once that happens, then we can start the Jupyter server. So you might be familiar with an event log. If you click on that button as you're walking it through, you might see a log that says things like this. So I did this just early this morning, trying to get a snapshot of how long does this take. So you might get warning saying 0 of 2 nodes available. Well, what's that mean? It just means that always running, 2 computers are always allocated, and they're hosting the Jupyter Hub software. They're just running in the background to be available to receive your request. But they're not sized right. They're not configured right for our container, our pod, which is our Jupyter Notebook instance that we want to run, or Jupyter Server instance. So it's saying they're not available. Okay, well, I'm going to respond. I'm going to trigger a scale up automatically. We're doing this on Google Cloud. I'm going to create a new instance in the Google Kubernetes cluster, and it's going to be a size that we've configured. And we've configured this, you can have up to 100 of these nodes. And so what's going on, I'm assuming, is you're watching a number of machines being provisioned. Those machines take a moment to install. And so you can see the time code, right? So this is at 5938. I had to wait till 0025. I had to wait a minute to create that machine. And I want to make sure you understand what's going on here. It's the equivalent of taking a hard drive, formatting it, installing an operating system, installing all the software, and saying, here, go. So it does take a minute, but it only takes a minute. And at that point, you have a computer. You have your unit that exists, and we're going to try and run some software on it. Now, there's 2 layers. There's the sort of the lower level operating system. So that gets downloaded, and then a container sits on top of that has all the software that we run. For the M2LINES deployment, the default here is the Pangeo notebooks. And so that software needs to be downloaded from wherever it is onto this brand new node. So you can see the time code again, 30 seconds, a minute 30. It takes about a minute to download this data. And then once the data is downloaded, it starts the container and spins you up into a loop. Okay, so hopefully at this point, we have several people who have been able to log into this thing. Now, there's something you can do if you go to the file manager and go to the hub control panel. You can sort of see what's going on. Now, for everybody, this is what your hub control panel looks like. It's pretty boring. It allows you to go back to your own server or stop your server. That's all you've got. For some people within M2LINES, you're a hub administrator. So you have a little bit more insight into what's going on. Because I'm on the 2I2C side, I've got administrator access, but so do at least a few people within your community. So we can go off to admin, and I can see who's using the server. Okay, so what do we got? So there we go. There's a user, another user, another user, another user, another user, another user, another user, another, oh, that's me. There we go. Another and another. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 or so machines or um, containers now running on this infrastructure. And it took a couple of minutes to spin up, but hopefully that all makes sense of what's going on behind the scenes. Once that infrastructure has been spun up, if you were to shut down your server and then immediately go on again, it doesn't turn things off instantly. It sort of has a cooldown period. So if you shut down and restart, it may come up really quick, meaning like tens of seconds. If you shut down, walk away for a few hours and come back, it will have cleaned up all this infrastructure, scaled it all back down to just one or two machines. So you might need to wait the sort of the 2 minutes to get going. So think of this as sort of the soft start in the morning. Come in just like in the days of old where we turn on computers and they boot up, that kind of model. Come in, boot it up, go get the cup of coffee, come back, and you should have a working environment. If it's taking longer than 3 or 4 minutes to get going, let me know, because I would like it to be so it's no longer than that sort of booting up of a traditional machine. It shouldn't be taking tens and tens of minutes. If it is, I'd be suspicious that something isn't right or wrong. Now, I go on to all of this just so you know what's going on behind the scenes. It's actually not necessary to use the hub to know all that. So I want to talk about 2I2C's shared responsibility model. This is sort of the structure we've got. 2I2C is not a vendor in the sense of Amazon or Google or Microsoft or any of the other companies who provide Jupyter Notebook services. It's not just you pay a credit card, you get so many CPU cycles. The way that 2I2C has structured itself as a nonprofit is to really have communities be partners with us. So when we talk about the shared responsibility model, there's always this interaction between what 2I2C handles, the Kubernetes, the cloud configuration, handling it when and if it goes down, and what the community does. So in this case, M2LINES, they're responsible for doing the science, but also facilitating what the environment looks like, what software is installed on it. And we work together in this middle region. So this is why there are members of the community, members of M2LINE, who have administrator access. So you can do things like see, well, did so-and-so log in? Can I change the software? And we're working together back and forth. So that's between the community and the engineering team. On a parallel track, there's also another angle, which is between the community and what we're going to call the community guidance team. And so right now, the community guidance team is me. Hi, I'm the community guidance team in this new role of product community lead. One day, maybe it'll be me plus somebody else, but today it's me. So what's my role? My role is to make sure the documentation's up to par, co-create content with you like this tutorial. Maybe in a different, these slides could be delivered by someone within your community. So I'm happy to work together back and forth. If there is a technical workshop that I don't need to present at, you just want me to show up and be present in a quarterly or annual meeting going, yeah, James, come by, just see how we're using the tool so we can gripe and share what's working well and what's not working well. I'm happy to participate in those kind of things, but it's really a conversation between what the community and the community representatives need and want and try to move forward, and then what 2I2C is able to collaboratively make happen. And so that's what we mean by collaborative. It's a collaboration between the partner community and 2I2C. So that's the way that 2I2C is thinking about this. It's definitely not a pay your bill and your invoice and we disappear. It's we get it up and running, we're pay attention to the engineering side, but we're also very vested in your success. I care, I wanna follow, I'm trying to learn what you're doing. We have lots of communities. I'm only one person, but this is my game. I like this stuff. So I'm trying to follow along and make sure we build something that's very useful for you. Okay, so the way I want you to think about 2I2C is that sort of data engineering or cloud infrastructure person within your research group, right? You might have that internally if you were a large organization, but imagine 2I2C as being that the person, the individual you can call on being like, the cloud server's down, what do we do? That's our expertise. So you can focus on your science and we can all move it forward. Okay, so that's sort of the broad overview of what is this software that you log into. How do you use it? Now, I did get a helpful email from Ryan Abernathy, who can't join us today, but as you know, he's the guru, has really been at the forefront of motivating this Pangeo community and trying to get big data and this sort of cloud first way of doing science. Been a strong advocate of that for a number of years. And he gave me some advice. He says, okay, in this session, in this tutorial, here are some of the things that I think are important to share. I want to make sure I explain to you what the 2I2C service is, what this managed Jupyter Hub is. Of course, I would not presume to teach you the science. You're the experts in the science. I want to just talk about some things about how I use these kind of services, things like starting and stopping the servers, what machine types mean, how to open and close notebooks. I want to do a little bit on Git and GitHub, just making sure you have that facility, you know how to use it, especially on the Jupyter Hub. And then we'll talk a little bit about how environments work. Okay, so if you need that background, like Jupyter is new, you're like, I don't know how this stuff works. Git, I haven't ever used Git before. There are a number of tutorials out there. Here's a relatively recent one from a guy named Fernando Perez, as in the guy who originally wrote IPython that became Jupyter. He's still involved in this space. It seemed like a nice reference to point people to if you needed that sort of baseline knowledge of how this all works together. So it's a Jupyter book. You've seen this before in M2LINES in terms of your things. And so it's got a little bit of an overview of what Jupyter is, right? Jupyter is a way of interactively working with cells, and you can execute things by doing Shift Enter, and there's a bunch of shortcuts. But more than that, it's more than just an editor. Oh, he's saying hi. You're able to do this very rich interactive output, so you can put images in there. And well, his code's broken somewhere along here. You can put LaTeX in there. You can put audio in there. You can put videos in there. You can put code in there. So these are all things that the Jupyter environment supplies. And then the other part of this book that I'll point to is just Git itself, right? What is Git? So Git as a concept, and again, if this is all pretty straightforward to you, I apologize for the review, but I want to make sure we're on the same page. When we talk about Git as a thing, it's an example of a version control system or a revision control system. Sometimes you think of these things as change management. Okay, so what does it do for you? What's the advantage or the purpose of it? What does version control give for you? Well, it gives you a backup. That's one. So something which is not on your local machine or on one instance of the cloud, it's somewhere else. It gives you some freedom. It gives you the freedom to your code, your writing, your paper, your talk, and just try something, completely go in a different direction, branch off your thinking, and be like, nah, it didn't work, and back out completely safely. And it also gives us a mechanism, an actual way of collaborating with our peers, both in the short term, you have multiple people collaborating, say, on a paper right now, but also over time. Someone could write a paper, you're like, hey, that's a cool idea. I want to extend it all the way through. Does someone have the link to the Jupyter notebook James is presenting from? Yeah. Here, I'll drop that in the chat. This is just, like I said, it's in the notes that I'm sharing here. So all the way through. So this idea of GitHub, the links is important. So let's do some of this. Okay, interactive. Right, talking about Git. Want to make sure it's all there. There are lots of presentations out there that talk about what Git is and how to use it. So here is just one of many. The idea here is you've got a number of different repositories. A repository is a collection of things. It might be all the files related to a paper, everything related to a grant, a research project, or maybe a course that you're teaching. And you have several different repositories typically you have set up. Each one of those repositories is actually a whole collection of files. And what it's doing, what Git does, is it takes your entire file system. So all of the different files and directories, the parts that make of it, and it thinks of the entire file system and snapshots it all. And it gives you a unique identifier. Sometimes we call that a hash. It's a snapshot of all of the parts that make up the repository. So it's not just it's not a collection of files, it's the whole file system tree as a thing. Now under the hood, what that's done is it's split up to a bunch of blobs that's managed by Git. And what a repository is a collection of these snapshots or these hashes all put together in some sort of linked list. So we talk about a commit history as being a sequence of versions of the entire file system tree. Now, there's a bit of math behind this. You can think of this as a directory acyclic graph. That's what's going on behind the scenes. It doesn't matter what version of Git you're using. They all have this concept that they're imaging the entire tree. It makes branching or splitting off new items in this linked list very, very cheap because you're not copying the data. You're just copying the references to the data. And if any of these blobs don't change, there's no need to make a separate copy of them. So branching and cloning is branching is very cheap within the same repository. And then the rest of this document goes into some information about how to use Git on the command line. You know, if you've never used Git before, knowing how Git works on the command line is really nice for having that deeper understanding of how to use it. But if we're in Jupyter Hub, we can use Git as well. Oh, I'm going to jump over here. So here's what we're gonna do. I'm going to do a little bit of activity. I'm going to make sure that people understand how to start and stop a server, right? Explore what's going on. And then once you've got that working out, what I'm going to get you to do is fork this tutorial, the one I'm currently presenting on. So I'll just put that in the chat in case it. Fork that into your Jupyter Hub instance, so you've got your own local copy to work with, and we'll talk about it. So let's just go through these activities. So as I said, at any time, you can either go to the File menu, to the Hub Control Panel, or jump to this thing, and we can stop your server. Now, this is a live demo, so I really hope that the act of me stopping this isn't going to break everything on my end. So it's shutting down my server right now. So if I find James, where am I? I wasn't here somewhere. I can't find my own name. That's fine. I don't need to find my own name. The system is shut down, so I can go to start my server, and you have all these server options. Now I'm suggesting huge. All of these are just allocating different amount of CPUs, and here are two instances that have GPUs associated with them. So if I hit start, it's going to go through that process. Okay, here we go. There are 12 servers spun up. We need to scale it up. We're going to need a new one. I was really hoping that I would just be able to claim the space, but maybe someone snuck in there on me and spun up their own machine when I gave it up. But you can see how it's spinning up now 12 machines, not 2 all the way through. And I said, I'm expecting about 2 or 3 minutes for that particular scenario to go through. Okay, so we can go through this. You can shut down and restart a hub instance whenever you like. It's not tied to your browser session, right? So to get to this page, this is just a line, a URL, and I'm authenticating through that login page that does through GitHub. If I'm running this, say, on my desktop in an office environment, I can just close down my browser, go to a laptop because I want to do this at a cafe, go home, go to the beach, go to wherever, and go to that same URL and reconnect back to this same hub. It's not going to turn off on you while you're not using it. Now, there is the functionality for some of our hubs. We say cull these servers, right? So it is possible for us to configure things so that if you're not using a server for a couple hours, it turns itself off. From what I can see in the configuration details, I think these servers keep on running unless you turn them off. So for the sake of sharing resources, when you are done with a server, you're done the day, just like saving power by turning off your desktop computer, what you would want to do is you'd want to go to this hub control panel and shut it down. We do cull Python kernels. If the kernel isn't doing anything for like an hour, then what will happen is it will be shut down to free up resources within your cloud. Oh, we're getting, we've triggered it up. Let's make sure that I get a node back. This is the dangerous thing about doing things live. We'll figure it out if it doesn't. I'm sure we can get it to work. In terms of culling, so you turn this off typically to conserve resources, but that does mean that I think right now it is possible that if you were to turn on a server, allocate one of these machines that used a GPU and a bunch of OSs, and then walked away for 5 or 6 days, it would just sit there continually running. We can change that if we need to change the behavior all the way through. But the idea is I think right now is to manage those. Why do we do that? So that you can have an environment set up for maybe a day or a weekend or while you're running things. And definitely so you don't get the situation where you're in the middle of giving a talk and you can't get your system to come back out. So that's weird to me, but that's just fine. But you know what? We have admin privileges. So let's see what we can do about why this isn't working. Access server. Let's just do the event log. Now this is going to be bad. See, this is one of those ones where I'm still trying to figure out why that doesn't work. And though I work with the cloud engineers, I am an amateur cloud engineer. So my guess is we're trying to scale up and we've just hit some sort of capacity issue. Oh, it did it. It did it. There we go. And maybe potentially someone shut theirs down to help me along. I appreciate that. This should scale to as many as we need, but it's not obviously for me. Anyways, normal behavior. And as I said, what's going on is behind the scenes, the system is trying to allocate no more machines. Okay. One not ready. Well, that's fine. 0 of 12. Why can't I spin up a new one? Yeah, so in terms of, there's a question in the chat about the cloud resources sitting idle, but the Python kernel getting canceled. Every notebook you spin up has its own Jupyter, has its own Python kernel. So you might have an instance, a notebook server, and it's possible for you to be running 10, 15, 20 different Jupyter notebooks at the same time, each one with their own kernel. And so that's taking up resources on your notebook server. And so the culling is, well, you haven't actually been running that notebook. It'll turn off that kernel instance, releasing resources back to your environment. And then, but that's different than the entire system, which is currently what I'm trying to spin up again. Oh, it seems like this is an issue. Yes. So, Drev, you asked me to follow up. Have I explained that enough, or do you want to jump on the chat while I'm waiting patiently for this to get going?
I was just wondering if I can unmute myself and ask the follow-up. I guess the bit that I'm confused, there's sort of two things that I'm confused about. So one, you said that I could, be doing some work in my office, turn it off, go to a coffee shop, and be able to access it again.
Yeah.
In that, what is that duration? Like, when does the Python kernel get culled? Like, do I have 10 minutes?
I think it's configured to 1 hour of inactivity.
Okay.
And again, that's a setting, and I'm going to forget which YAML file that is, but it is one of those which has a setting which is a kernel culling. But we can change that if we need to. So it helps things not sort of gum up the works, let's say, right? Because you can imagine someone trying to open a whole bunch of notebooks, and over time that starts to consume all the resources on a node.
Right. Yeah. So that's what my follow-up question is. So let's say that two members from M2LINES come and they open up their separate instances or whatever we call it. Are those shared in some way? Because let's say, like, if I am running virtual machines that are completely independent from the ones that you're running,
yes,
why should the M2LINES community care if I've gunked up my own bit, right? Like, I'm the one who's responsible for it. So.
Well, I think in terms of a setup, the users of that, you got a whole spectrum of users, right? So this would sort of be the default case that would work for most. So you can imagine that there is a user who doesn't quite understand that they need to manage their resources quite as carefully. Now, if those kernels are doing anything, right? If they're actively doing any work or any processing, they're not going to get culled.
Right. No, but I guess what I'm asking is that, like, when I go on, if I've asked for like 12 virtual machines or like a huge server or something,
yeah,
and you come in through the M2LINES community as well, if I'm not using all 12 of them, are you sharing some of them with me? And which is why it makes sense to kill these kernels? Or like, if
no, each container is living in its own private space. So when you spin up one of these machines, that is your own private allocated thing. So if it says you're allocated 32 processors or 16 processors, those are yours. There is no one else in that allocation, which is partly where I'm getting stuck in right now. No,
right.
I just texted my tech guy and was like, well, I can start it. Don't you hate that? I'm just going to try something which I hope is not going to throw me off. Ha! You can't stop it because it's not working. Well, that's a terrible sort of thing. Let's just keep on talking for a while and we sort out the technical issues, which is a nice thing. I have this loaded up here. Okay, so next step, and I'll get you to sort of continue on doing this thing as I work out my own technical issues, because that's obviously embarrassing that the presenter can't get it to work, but hopefully it's working for you. So once you've got that sort of idea of being able to start it, I want you to try doing a forking of a clone repo. So you see down here, you see this icon right here. This is the icon for GitHub. If you were to click that, and of course that's not going to. Oh, it is working for me. That's awesome. If we were to go to your home directory, and of course this won't work because I don't have an active running machine. Relaunch. Come on, you silly. Yes, I know it's not running. If you were to go to this tab right here, one of the options that should pop up is the ability to clone a repository. And so if you clone that repository and then copy and paste, yes, I know that's not working right there. Thanks very much, software. I'm totally aware that that's like that. Very frustrating. What you can do is you can clone a repo, and the repo I'm going to get you to clone, yes, I know it's trying to connect to it, is the 2i2c-m2LINES repo. And once you've done that, you'll have, okay, I'll do two things. I should ask you to go to this repo, fork it first, so that you have the ability to clone another one, that you commit your changes to it yourself. And then what you can do is clone it, and we can talk about how to do some criteria, some pushing of code to it. Quota issues. And this is what I asked the group. I said, will I have any quota issues? Oh, no, you'll be fine. No problem at all. I have quota issues. Well, that just sucks, folks. Okay. Yes, I know. But you know what? This is where we Okay, we can flip to the GitHub version of this thing here. So what I want to talk about is the idea of making a commit within the Jupyter Hub environment. So I think what I'm going to do here is I'm going to use Fernando Perez's version of this, but it'll be very similar for you. And I do this only because this is a pre-rendered version of it, but you can do the same thing. If we want to actually not just clone stuff from Git, but then make a change on it, you have to have some credentials, right? People can't arbitrarily write information onto a GitHub repo. You all have GitHub credentials because that's how you're able to run into the hub. How do you get those credentials actually onto your into your Jupyter Hub environment to be able to do it? And a nice way of doing it is to have a notebook that has just a little bit of code, and that little bit of code says import gh scoped creds, and then %sign gh scoped creds. If you've been able to successfully clone my repo, the one that I'm using here as a demo, see that inside that repo is a little file called ghauth. That's GitHub authorization. And so what should happen is if you execute that cell, what will go on is it will give you a little printout, and it will say, in your clipboard, I've now given you an access code. Please go to this login or this URL at GitHub. So you click it, you go to it, you copy paste onto it, and then what will happen is it'll bounce you back here, and for the next 8 hours, any of the notebooks you open up and spin up on this system will allow you to push data onto GitHub. And so just to practice how this works, what I'm going to invite you to do is take some of these forks, and I see people have been making forks, so I know that's working. I don't want to fork it. I want to go to the forks. I want to go to some of these forks. Try and see if you can add a file, add a README, make a change, and see if that works in terms of getting it to go. Yes, I know it's not right. So this is one where, there must be a quota issue. So even though it says 100, which is what I went, it must be limited to 12 UJs. And there's another 12 people in this group who've already been able to spin it up. I see a comment in the chat. Yeah, you can spin up a smaller one, that's for sure. I just had a demo that was going to work better with a bit more resources. So we got a usage issue. So, come on. I know what I'm going to do. I have a thought. I think I can use one of my colleagues' machines behind the scene and spin up a slightly smaller one. Maybe that will work as an option. I don't know which first. Apologies, everyone. It's one of those things where sure like that to work smoothly, but it's not working smoothly for me today. Okay, so in terms of could I use Leap? No, I haven't prepped the data on Leap. So I did do a bunch of preparatory work to get things working in this environment. But there's still lots of things that you can do in terms of playing around with it while I get this sorted out. So GitHub, being able to push it is definitely something that I want to make sure people know how to do. And it should be as simple as, well, come on, just any one of these servers. Come on, guys, just something. Well, I know what I'll do. Dhruv, can I just
go for it?
Can I just become you for a moment?
Yeah.
Beauty, is this going to work? Let's cross our fingers. This is going to work. It's looking like it's going to work. Woohoo! Okay. So you see what's happening here is I'm actually logged in as Drew. Well, this is going to be a test whether or not it'll work when I'm using someone else's code. But Drew, thank you very much. This is probably the right solution. So I'll just jump in and use this code. Okay, so demo number 1 was we can figure these things out, and I've now learned that this system is configured to a maximum of 12 huge instances at once. And so when you're number 13, you're out of luck. We will look at that, and if we need more resources, we'll get more resources. But we're back on. Okay, so we've talked about what the hub is. What I want to do is I want to make sure that people know about GitHub Scred. So the idea here is if you're in this button right here, this is what I want to show. You can make a change to that file. So Drew, thanks very much. You have created a new file. You called it try changing. And the way that Git works is you Drew, you're working on a small? Well, this will be fun then. But you know what? We'll persevere. We'll get through this. You created something, and so the way you push that back to your repo is you'd stage it. So one of the models of Git is all of the changes you do together are one large, one set of commits that work as an atomic unit. And so you stage things, and then to commit them to your repo, trying to make a commit, right? Some comment about what you've done, and then you commit it. Now, when you commit something, what's gone on is it's actually committed it to the repository, which is sitting on the Jupyter Hub server. To get those changes to be reflected back onto GitHub, we have to push those changes all the way back up. Now, it failed because, Drew, I think you haven't yet allocated access to that machine. So what we would normally do, and this is one where I'll invite you to do it, but I won't do it for you, is I would go to this GH auth thing. I would run this little guy. It would say, here's a code that's been copied to my clipboard. I hit GitHub login device. It would jump me to a page that looks like this. I would copy paste something in, and I hit continue. But it's going to get weird because I'm not sure that those credentials map to your account. So we're just going to play with that. But the idea is once doing that, you should be able to push those changes back up to GitHub. And so it doesn't matter whether or not you're working with, you're familiar with Git on the command line. You also can do Git within the UI. And so this allows you to make those changes to these repositories back and forth. Okay, let's continue on. In terms of what you can do on this site, we can download lots of different notebooks all the way through. So looking through the M2LINES literature, I found this resource that I'm going to assume many people on this call are already familiar with. And that is this Jupyter book that you've created called this machine learning with the Lorenz 96 model. So for me, I was spending time over the weekend going, well, this is cool. This is really cool. Oh, I really like this stuff. And so I was thinking that we could play around with this model for a moment just to see how this stuff would work in practice. So how would you do that? Well, what you would do is you would start by taking this repo and cloning it. So what do we do? Well, and again, Proof, I thank you very much for lending me your resources for a moment. If I go to the GitHub tab, what I can do is I can clone a repository, and I'm going to copy and paste this first. Copy, clone, and that's going to make a local copy of all of the code to do with this Lorenz 96 model into my local disk. Okay, so there it is, L6 novel. When you're cloning things with this authentication, you want to be using the HTTPS version of all the URLs. This is not really something we're going to use SSH for. If I had push access, if I had write access to this folder, then I would be able to commit to it and push it. I know, Drew, I don't think you have write access to this folder, or maybe you do. I'm not entirely sure. But here is some code that we can play with, some machine learning on the hub. So this is my snapshot into what I think is going on the back end, making these resources work. So there's a bunch of notebooks. So if we were to pick one of these notebooks we wanted to play with, let's say I want to do something with neural networks. That sounds like a cool and fascinating machine learning kind of application. I could open up that notebook and then I could start to run it and work with it. So this would be an idea of collaborating on the cloud. The shared copy of something exists in GitHub. You're creating a local copy of it. Maybe you're making a fork of it first, and then you can start to execute the code all the way in there. Now, when I try and execute this library, if you've done it on the small, medium, large, or huge versions, you're going to see a problem almost right away. And the problem is Torch, as in the PyTorch library, is not part of the base image that we downloaded when we started this all up. So I want to talk about what I mean by those images. Okay, so these images, when we create something in the hub, the actual code that we are running is the Pangeo notebook Docker image. It's the container which has all the software. What goes into this container is managed by the community. It's managed by your group. Now, we set it up and you've chosen just to use the standard Pangeo notebook, which works great for lots of things. And it's got a ton of really useful software already loaded into it, Xarray and Dask and graphing libraries and a whole bunch of cool things. The Pangeo Docker images allow you to think about your software as having a whole bunch of layers. So if base notebook is Jupyter, Pangeo Notebook is Jupyter plus all of the great libraries that are used in the earth sciences. And then there's a few other notebooks which include everything again, which is over and on top of that. In particular, there is a PyTorch notebook, which is the PyTorch framework, and an ML notebook, which I think is a TensorFlow notebook that you could spin up an image of. So when we went to that initial page and we chose start an image, and you could choose small, medium, large. You remember at the bottom there was two that allowed you to do a GPU. Those are backed with a PyTorch notebook, which would have all of the PyTorch software set up. So that is definitely one option. One option is to go ahead and use a container image that has PyTorch already installed. The other thing we can do is within this virtual machine, remember it's your own private Linux machine. It's not being shared by anybody else. You are the only user on it. So when you go to the terminal and I ask, well, who else is around? There's no one else there. Like the only user on this machine, the only thing running is you. Like it's your Python shells and some Git remotes and that's it. Oh, by the way, who am I? When you're working with Jupyter notebooks, you've seen this word Jovian. Well, you're Jovian. You're a user of the Jupyter. So the username for everybody is Jovian. But there are no other users on this system, right? So if we go up a directory, just like in normal Linux, there's a home directory. The only user here is Jovian. It is the username for any user who happens to be on the system, but you're the only person on this particular node. You're not sharing it. It's allocated to you for the duration of time in which you're using it. Okay, because it's your own thing, you can manage your own environment, your own Conda environment. So for something like that L96 demo, okay, you'll see in here that there is a full environment file, and there's also something called a Conda lock file. What we can do is we can use that Conda lock file, and I'll just show it to you for a moment. Okay, these are all of the packages, specifically the actual packages tied to certain hashes, which are needed to run any of the notebooks in this package. And even though there already is a environment set up called notebook, it's the default notebook, what I can do is I can go to Conda and then I can create I can create. I don't want to create. I want to create. I want to create a new environment under a certain path, and I'm putting it under a spec. We'll call this the L96 environment. And what that's going to do is bring in all those files. So a command like this, conda create in a certain directory, this file, what that will do is create and download onto your private system all of the software needed to run that document. Now, this takes a moment, right? Because you're setting it up, you're copying files onto your own local space. But once this is completed, what will happen is we will get a new kernel appearing up here, and you'll have the choice between both the default kernel and this new one. So you can have a new environment to play with. And so this is nice because I know that we're working in computational science in the Python ecosystem. Everything's always changing. Someone comes up with a new library and you want to test it, you want to play with it. Because you can manage your own Conda environments in your own space, you are more than welcome to test out any software you like. These files are being installed or downloaded into storage space on your home server. And those files will persist because they're living on a stored bit of server, and anything in this directory, anything in that home directory, these files are going to live and be available every time you start up a Jupyter instance. MKL, the math kernel library, is the biggest chunk of this, so this is taking a moment to run. But once we have that run and it finishes, what you will see is a second kernel here allowing you to get the Torch software. So here's my summary. If you were trying to work with a notebook and there is a library, like a Python package or something that you don't have, you can create and maintain your own Conda environments. You could also use a different container image that maybe has their own environments. Those are your two options. Now, here's a bit of a caveat. The amount of file space actually on this server, like when we go to the terminal and I type in commands, I'm at a directory, a home directory. I think there's only about 10 gigabytes allocated to each user. Okay, so when you create it, you have 10 gigabytes to play with what you want. It's designed for notebooks, scripts, very small data sets, environment. All this software can get a little bit large. So let's just take, oh, it's still loading. Yeah, that's fine. It can get a little bit large. And so if you end up having 2 or 3 or 4 large environments, you have PyTorch, you have TensorFlow, you have a few other Conda environments installed, you may encounter a problem where you start to run out of space on your home environment. Here's my recommendation. Treat environments, Conda environments, as being ephemeral. Spin them up, delete them, create them, destroy them. Like, don't worry about them being something you've got to keep forever. If you find out that as a community, several of you are like, oh, you know what, this base image is using version 14 of the library, and we all want to upgrade to version 18 of the library because it's got a cool new feature. As a community, you may want to manage your own image that has the Python and associated libraries that your community needs to use. And then what you can do is we can spin up a Docker image so that everybody has access to that as the base image. So you do have the ability to manage your own images like you would on a laptop. You can use Conda to do that. If a package is only available through PyPy, you can use pip install and that will put it into the Conda environment. So are we done here? Oh, now it's executing. It's all regular stuff. But that is something you have as flexibility in this environment. And again, once you've installed it, once I've created this environment, those files are living on my local system. And so they're going, or my local system, on this networked drive, and they're going to persist even if I shut down this whole image and come back to it. Or if I shut down this environment and start up a different size instance all the way through, it's going to work when you come back to it. So my assumption here is, at least with the M2LINES group, this Jupyter book, this machine learning with Lorenz 96, is that something that your community is using sort of as a shared resource to really explore out different ideas about how you're approaching innovations in machine learning and Earth systems modeling? Is that sort of how you're using this resource? Because if it is, it looks pretty awesome. I'm loving this sort of, here's a simple idea, and here are different things we can do with it. Is that how this community is using this resource?
Yeah. Hi,
Yep.
James.
Hey,
You can chime in, or Alex.
sure.
Yeah, thanks a lot. Sorry, I joined a little late.
No problem.
Yeah, so initially it was really as a tool for, teaching each other new tools. People coming from ML learning about, the LINES 96 and how we develop parameterization. And now it's for our newcomers to also learn what's going on, and really for the people coming from the physics climate modeling side to learn ML and to test out a bunch of new ideas, in a super simple framework. And hopefully, now it's open to the community, so for others to learn something from it and explore different tools.
It is doing its job admirably, because not being part of the specific community, was sort of like, so what do you guys actually do? And so I had more than a little bit of fun over the weekend going through several of these, going, oh, cool. Oh, really cool. Anyways, I'm really impressed. In terms of community building, documents like this are exactly what you hope is an outcome from these things. Okay, so my hope is you've already explored these kind of things, but just know that you can explore these kind of models in the Jupyter Hub environment. If you were to spin up an image on one of the GPU-enabled clusters that had a container with PyTorch installed, I'm crossing my fingers here. What should happen is PyTorch, of course, one of its features is not just machine learning, but it's also GPU-enabled machine learning. So we should be able to run some of these workflows on a GPU-enabled node. If that's not working, I'm going to call that an issue. Send something to support@2i2c.org, and we'll get that working for you, because that's one of those resources. So support@2i2c.org. If there are any of those infrastructure issues, I sent it as a direct message. That wasn't right. Let's try it again. Support@2i2c.org. Fire that off, and that'll get to a support team. Again, that's probably me in this case. And I've talked to the engineers about solving those kind of issues. But one of the advantages of moving some of your machine learning training into the cloud is you can let this machine, which is sitting in Iowa, do the work, and you don't have to burn cycles on your laptop and hear your desktop fan chewing all the way through. Maybe your workstations, you've got a fantastic graphics card, but if you're like me, you don't have a fantastic graphics card in your laptop. And so you can leverage some of this technology to have it run in the cloud doing its thing. So be aware there are some GPU-enabled nodes in the cloud that, and again, I'm crossing my fingers here because I assume this is how it works, but I haven't actually played with it, though I will after this. But if it doesn't work for you, let me know, and I'd like to make it work. Okay, so at this point, that's the first half of what I want to talk to you about, is sort of a tour of what this environment is and what to do with it. Again, I'm assuming you're familiar with Jupyter Lab as an interface in Jupyter Notebook. Hopefully you've had a chance to go like, yeah, okay, I can see how this GitHub authentication credit thing works. And then the second part of today, I'm going to talk about files and data in the cloud. Let's just take a pause right here. I'm going to go back and try and see if I can get onto my huge instance, because that will be a lot more useful when I get to the second half of this demo. Is there any topic of conversation about the setup, the infrastructure, what's going on behind the scenes that this group wants? Any questions, I guess, is where I'm at. No questions. Never sure if that's a good thing or a bad thing. Okay, well, we'll just proceed on here. Pod triggered scale up. Let me just check my chat here. I've been communicating with one of our cloud engineers. And so my request to Sarah went in, about 20 minutes ago, 25 minutes ago, saying, help, things aren't working. And successfully assigned Jupyter. Yay! So we don't necessarily respond to requests in 30 minutes or less, but we do it relatively quickly. Yay! Okay. on to the hard part of the presentation, which requires a slightly bigger notebook. I should talk to you about support and what our service level objectives are within 2i2c. 2i2c is a distributed team. We've got people in the Western US and California, on the East Coast, in Europe. So we span multiple time zones. The expectation is usually within an hour or two. If it's within working hours, whatever that might mean for support engineers, we'll at least try to acknowledge the concern. And if it's an outage, like it's not working, we'll try and get on that right away. If you send us it's not working and it happens to be the middle of night or the middle of the weekend, it's possible it could take a day or two to get back to it. Our support model is not a 24/7, 5 minutes, we're on pager duty, but it is supposed to be responsive, especially for those critical outages where you can't use the service. If it's not working, the fix is definitely on us. But to be fair, a lot of the issues that one might encounter may actually be on the user side. A piece of software isn't working. And if it's a workflow that isn't working, what we might do is just bounce you back to your own community going, well, the infrastructure's working, but it's a problem with a library that you're not calling correctly. There are other opportunities for support for those. And I'm happy to work with this community to make sure you have access to those other ones. In particular, I'm thinking about some of the discourses, like the Pangeo discourse, I would recommend is a good place to go to ask questions of what you're running on this environment. Okay, and now I'm going to breathe a big thank of release because I have something. Okay, woohoo! Thanks to support people. Let's keep on going. So I'm going to jump into the Jupyter tutorial. Now I'm running on a machine with a bit more RAM because I'm not going to use the RAM, but I am going to use the CPUs on the back end. And again, feel free to test this out on your own time when you're ready. Oh, what are you doing now? Now it's spinning just to make fun of me. Okay, good. Sounds good. Okay. One of the features of doing any kind of cloud computing, I believe, is really thinking about where the data is on these problems. So I want to spend the second half of this tutorial talking about files and data and the pros and cons and some of the challenges that we have and opportunities when we talk about files and data in the cloud. Okay, so the first thing is I've already addressed that there you do have a home directory, right? So when you go on the left to this file browser, these files here, these are things that are sitting on your home directory, and you can use the file browser to interact with them. You also could use the command line to interact with them if that's more your thing, right? And the idea here is you've got a file system, and from this file system, you can move things. So right now on this machine, because I've got some libraries, because I installed some packages, I put some data up here. I've got like 5 gigs worth of data up here. And I think I'll hit a capacity limit when I hit 10 gigs. The data in this home folder is designed for scripts, code, notebooks, and small files. It's not meant for big data, but it is persistent. So if you do need to load something up or down, you can go from here and you can right click on something and you can download the file, or from your home drive or your whatever file system or operating system you use, you just drag and drop it into this file browser or upload, or you could use a web UI tool like this upload thing. I'm not sure if that popped up on the screen share, but you could upload files into the space. That's one method. Another method is you can use command line tools. So SSH exists, SCP exists. So if you have data on a remote server, say a high performance computing system, you could set up an SSH key and from the Jupyter Cloud, reach out to that remote server and pull data. One thing, unfortunately, you can't do is we don't have an SSH client running and with a port open to the outside world to be able to get to this machine. If you're good with SSH, you know how to reverse proxies. I'm sure there's a special way to make that work. But the design here isn't to SSH into the Jupyter Hub, but you could, from the Jupyter Hub, SSH out to be able to retrieve some data. So that's one way of getting data in and out. If you've got a lot of data, okay, but in more than a few gigabytes of data, what you want to look at is something called cloud object storage. Okay, that is the method or the way the data should be stored when you're dealing with things in the cloud. So I want to talk about this a little bit so we can explore what our options are. So I've talked about the Jupyter Hub file system. And again, you have a home directory, and that home directory, your username is Jovian, right? It's a persistent network attached drive. There is a shared drive. So if within your group you had some file that you wanted to contribute back and forth, you could put something in shared, but that's a read-only file system. Only administrators, and there's a few of you on the call who are administrators. If you're an administrator, you have this new bonus directory called shared read write, which is a writable version of the read-only shared file. So if there was some like data set that you want to share among multiple people, that's somewhere you could put it. Maybe there's some data which is not in GitHub. There is a temporary directory. So on the terminal, we can talk about what's in the temporary directory. I don't know about you, there's nothing in it right now. One of the things that I like to do is I like to make a symbolic link from the temporary directory to that home Jovian directory so that it pops up in my file browser. Hopefully this is going to work on me. There we go, there's temp. So this is what's called a symlink. If I go in that directory, this is now mapped to the temporary directory on the machine. Now, why would you need a temporary directory? So this temporary directory, first thing, it's a fast SSD drive. It's local to the machine. It is much larger in terms of space than the directory is. It's order 100 gigabytes of data. So if you need a bit of scratch space, local file scratch space to do some calculation, that's a good directory to do it in, right? You got some intermediate file, it's gonna be 75 gig, you need to put it somewhere. You're welcome to use temp, but it's not persistent. When you shut down the server and restart it up, that /tmp directory will get wiped, but it could be convenient. Another place to put data, if it's appropriately sized, is you could use Git or GitHub, right? That's definitely where code should put in. We should move code in and out. And sometimes it's appropriate to put some large files into GitHub if they're not gigantic. Maybe a few, like hundreds of megabytes, it might make sense. And again, this is the documentation I was talking about earlier about GH scope creds as a useful tool to allow you to authenticate against a server, against GitHub, so you can just push and pull back and forth. So those are all fairly classic ways of getting data to and from a server. Let's talk about something which is unique to working in the cloud, which is cloud object storage. So because this server is set up on Google Cloud Platform, the name of the cloud storage that they use is called Google Cloud Storage. That's what it is. That's what's been set up. Amazon has their own. They're called S3. I can't remember what all the S's are, but basically it's a storage model. Azure has its own cloud model. It doesn't matter what cloud model you're dealing with. What cloud object storage is essentially a key value pair storage system. And what's going on is the reads and writes to that storage system are fundamentally happening over the web. They're happening with a REST API, HTTP type requests. The way that the cloud works is fundamentally different than a block file system. It's a traditional sort of POSIX standard. I open the file, I read bytes to it, I close the file. It has much more higher overhead. It takes a fundamental amount of time, like tens of milliseconds, to go to or get from data across the network. It is not as low latency as an SSD or some other local storage. But here's where the feature is. Cloud data scales out. So a cloud server is not one CPU talking to one hard drive or one computer talking to one hard drive. It's a distributed storage system that can have many hundreds, many millions of computers concurrently reading or writing from it, right? So on the back end, this is how like Netflix or Disney Plus is able to serve all of those movies, right? The actual videos are not stored on a file system like you and I would have it. They're stored in some sort of object storage where behind the scenes, it's a bunch of key value pairs. Now, set up for us, there is a Scratch bucket. Anyone can write to it Google Cloud Storage bucket or container set up within the M2LINES environment. Not all of our 2I2C environments have that, but ours does. You've already got credentials set up to be able to use this Scratch bucket as a place of putting data to experiment with cloud storage. Now, it is not for permanent storage. The Scratch bucket here automatically will purge its data if it's not after 7 days. So slightly more permanent than /temp. So it's good for experimenting. Say you've heard about the czar thing in cloud data, you want somewhere to put something, that's where it could live. It's not for sharing data permanently, but if you're trying to set up some sort of demo for someone, and it'd be really nice to have a good chunk of data in the cloud already ready to go, you could use the Scratch bucket. So that was my scenario in preparing for this session. I wanted to get some data, some high resolution model data, put it somewhere in the cloud so we could use it. So I just used the communal Scratch bucket. So the data will sit there for a while. Now, if you want to use this Scratch bucket, there is a environment variable called Scratch_bucket, which gives you a path that you can use, but it's a shared thing. Anyone with credentials onto the system has access to this bucket. Now, this is going to make a lot more sense if I give you some example. So I'm going to do an example and I'm going to pick some data set. We talked earlier about L96 as it was really obvious to me as an outsider that that was a community resource for teaching someone how to do machine learning on this really simple two equation model, the L96 kind of model. But if I'm right about it, where we're trying to go within this environment is we're trying to go to sort of, we want to do that kind of thing, not on a two equation model, but on a real model. And so I saw on the M2LINES GitHub repo on your talks page, I saw that Yanni and Paul, you've done a number of work with an atmospheric model, and you were kind enough, generous enough to make that code available so I could see what you were doing. You put the data up on Google Drive, and I was able to watch Yanni's talk on this. So I was like, oh, I think I know what this is about. Awesome example of open science, by the way. That's cool. So just using the output from that data as a proxy, I can get a sense of the kind of thing that your community probably is doing or has done or might be working towards. So in particular, so I can go to GitHub and I can clone a bunch of things, and I can see these different packages. And again, stop me if I'm misrepresenting it at all, but subgrid parameterization, momentum parameterization, this is all of the code for these different papers that Yanni and Paul have worked on, right? So what's in here? What's in a project in this field? Well, there's going to be some Fortran code which runs some high resolution model, right? So this is the SAM code. There is the actual Python code. And I'm going to assume that that's typically run on some high performance computing resource, right? Something with MPI, lots of interconnected nodes. As is very common, there might be some post-processing code out there. There might be some MATLAB codes, and looking through GitHub, I can see a lot of, I'm going to go back to this momentum parameterization, seems to be the most recent one. I can see this folder, high-res processing code, and I see a bunch of MATLAB code. And I said, I don't know who the original author is here, but I can see that it's very traditional sort of way of doing it. It's one large master script going on to 3,700 lines that I assume is run in sort of a batch way to do some post-processing the model, right? And if I understand it, you got to compute some tendencies, you got to come up with some coarse versions of the model, you got to create these data sets so that we can do some machine learning on it. And then what we have finally is a bunch of machine learning, right? So these are all the NNs, the neural networks, where there's going to be some training of various kinds, so there could be maybe some Python scripts. That's to load the data, and then to do some training, right? So these are offline scripts you might run, or potentially what you have set up is some notebooks. Let's see if we can find a notebook. I'll find it. Notebooks, plot notebooks. Online simulations, momentum production. Okay, and again, I'm just picking into one of your group only because they have done the kindness of making this somewhat public so people could do things reproducibly. And so what I went as I took a look at this data, okay, so sklearn, going to do some scoring, maybe some random forest type kind of stuff is going on here. He's got his data up here, and this is the code. This is the kind of thing we're collaborating on. Now, the way that I see, and again, apologies, it's only because I see your code. I see that you put a lot of your data up on Dropbox or up on Google Drive. And what I'm going to propose is there might be a better spot for that kind of data to live. So what I was doing is I took this data and I thought about how we access data in the cloud. There is this library called FSpec, which is trying to abstract the idea of a file system, but apply it to a whole bunch of things that are in the cloud. So FSpec is a library, Python library, that understands a lot of different models. It understands how to get things from Dropbox, over the web, from Google Cloud Storage, from Google Drive, from S3. It abstracts all of these different providers and gives it a file system-like interface. Okay? To access the Google Cloud storage bucket, what you would do is you would just import this environment. You all should have this environment set up, and it looks like this. This is a URL or a URI saying Google Cloud Storage, m/scratch is the bucket, and just for default, there's a number of different environments set up. So if you want to access that, we can use FSpec to connect to that Google Cloud Storage. And then what I can do is I can take those files and I can put things in them. Okay, so I can take a file from my local file system. And again, I am sitting here in, let's go up a directory. Not in GitHub, I want to go to M2LINES. I take this README file and I just pushed it up to the hub. And again, it's key value. So the key is the path to this thing. And in Python land, this would be GCS, M2LINES, scratch, jrow /readme. And the content is the content of the file. But it's just a key value mapping. So you also could use what's called a mapper and map a byte, any collection of bytes, to this key. So I can just take, this is my byte string, and map it to that. And now what I have inside my bucket are these files. So this is a key that corresponds to this data. This is a key which corresponds to data. So what do I mean by that? If I was to look at that, you get the byte string representation of what's inside of there. Again, key value pairs, think Python dictionaries. Now, because we don't all have, well, we all have access to the same things, but if you use Scratch Bucket, you're going to get your own username in there. There's nothing stopping us from looking at anybody else's stuff. So if I was to say GCS and then do a listing of GCS m2LINES.scratch, okay, these are all the directories. And I can see that, Andrew, you've gone and you created something in that space. And for some reason, I have two. I don't understand why I have two at that moment, but we can read and write each other's. This is a shared space. And again, it's Scratch. Now, I found Yanni's high resolution atmospheric model runs. They were available on Google Drive. And so I wrote a little bit of code over the weekend to take one of the outputs of the model and copy those files into Google Cloud Storage. So I wanted to put those files just in a shared directory, and I put them at this URI, scratch J-Monroe file ops. Because they're part of our shared environment, everybody on the M2LINES community has access to these things, and you can see them. Now, if you're doing this on the Leap cloud, you don't have access to the same credentials to get to that. It's on Google, so if you had the credentials, which just require a little bit of behind the scenes work, we could get to this file, but it's not automatically being set up. And you can see that what's in it is a bunch of key value pairs. So in this case, the keys are the file names. And again, I'm just assuming, because I saw so many references to it, that several people in this group are familiar with this model. And if you're not, it's just an atmospheric model, a water world that's simulating at a certain resolution. And this is a control run. And these are time steps of a bunch of variables that represent an atmosphere of a water world. So what is this data set? I said I just let it ran over the weekend, and I uploaded about 4,800 files, about 4 terabytes of data. 4 terabytes of data is just sitting in the cloud as scratch space. Now, this isn't going to persist for a long, long time. If you needed a shared resource like this to persist, we could create other objects within the environment. It's something that ideally hub administrators should be able to do on themselves, but work with us, we can come up with these spaces. There are providers of cloud storage outside of M2LINES that you could take advantage of. I'll talk about that in a moment, but it's just a place somewhere to hold files. And so I just spun this up to give me some data to work with to demo it out. Now, even though it's on the cloud and I'm working on the cloud, we still have to think about getting that data from where it is in cloud storage onto my file system. So what I can do is I can copy that file. And what I've done is I just taken all these files. I'm just taking the content of that key and pasting it into the root directory of here, which would be, one more directory out. It took about 15 seconds. So it took 15 seconds to download this file onto my local file system. Okay. Now, this file, that's its path. You can see here, if I do an ls of it, it's an 880 meg file. So it took about 10 seconds, 15 seconds to download a gig of data. So it's a pretty nice responsive network. You know, a gig every 10 seconds is not, this is a gigabyte, not a gigabit. So, you know, it's a decent network backbone. And once I have that file, I play with it any which way I could on a normal system. I could use X-Ray and open up X-Ray and then say, okay, I want to use this tool. So I can open up that file and I can open up the particular file, and we can see that what we see inside of it is, oh, I'm loading the library for the first time. This is where I had this all run, but I shut it down. Okay, what do we got? We've got this data set. It's a single time step of a 48 by 1400 by 576 domain atmosphere. So relatively high resolution. That's what, quarter degree? It's a quarter degree model. It's got a bunch of variables inside of it, right? We've got some water vapor. Yeah, some water vapor, and we've got some precipitation going on here, some thermodynamics. And with that one file, you can explore the file like you would, whether or not on your laptop or anywhere else, right? Given a file, you may want to take a look at it. So let's take a look at what's in this water world, right? So I'm just using the X-array tooling and the accessor functions and a package called hvplot to visualize this really quickly for me. And I can see right away that, well, in this world, the water vapor is highest around the equator. As I go up into the atmosphere at a higher and higher height, there's less water vapor. I guess that makes sense. It's warmest around the humidity. Maybe I want to look at the non-precipitating condensate. Is that just a fancy way of saying clouds? I think it's just a fancy way of saying the clouds. So within this one snapshot, what we're looking at here is where water is in the atmosphere of this planet at this particular point of time, because this is only one file. Maybe we want to look at precipitation. So again, here is the same structure. And so I'm looking at the data and I'm seeing that this is where the rain and the snow were actually falling at this 100-day into the model, right near the surface. And I look at this and I see that there's some structure in here, right? So if I'm just exploring this model for the first time, I may be like, okay, those sort of look like thin wedges. Are those sort of like fronts of some kind? Well, let's take a look at the temperature field, right? So look at thermodynamic temperature, and you can see right away that there seems to be this high correlation between where the temperature is quickly changing and where it's raining. And I guess that makes sense. My atmospheric science is very general, not specific, but you could explore data like you normally would. Okay, so let's say we have some data and we want to start to now deal with this data because we're going to use it to do some training of some machine learning product. We want to work with this data set. If you do it like this, taking data that lives in the cloud and downloading it to a machine in the cloud, that's no better than just downloading it locally, okay? It took about 10 seconds to get this file, but this is a 4,800 time step data set. It's going to take you about half a day to download this data onto some disk. And you're going to need 4 terabytes of local storage, local file storage to be able to do it. So this is the wrong approach when we're talking about cloud computing. When we're talking about cloud computing, get out of the mindset of I have to download the data. If downloading the data is in your workflow, maybe it's the wrong workflow for cloud architecture. Okay. The idea is the data is already up there in the cloud. We want to push our computation to where it is. Now, that's the big idea of cloud computing, or at least one of the big ideas. We want to avoid downloading this data to be able to analyze it. We want to bring our analysis to where it's located. It's allowing us, and you've heard Ryan Abernathy's talks on these, right? It's allowing us to tackle problems which, if historically were either just frustrating, hundreds of gigabytes, a few terabytes, it's allowing us to do problems which are fundamentally impossible to do with local infrastructure. You got a 100 terabyte data set, you got a 20 petabyte data set. There is no physical, practical way to download that data locally, whatever local might mean in your context, to be able to analyze it. Instead, bring your analysis, your code, your script, your training to a compute center which is network proximate or cloud proximate to wherever the data happens to be. So if you're doing something and the data is living in Amazon's cloud system, you probably want to be running your data on an Amazon cloud system. So if you have a bunch of data that happens to be on S3, running it on Google Compute is going to be okay, but not great. If your data is on Google, then you want to be running it on a Google Compute system and just bring that code, again, using GitHub to push it up. Now, I think this group had a talk or a presentation on PangeoForge about 2 weeks ago, maybe 3 weeks ago, where you were learning about this, trying this. And PangeoForge, the model, the idea is we're going to treat data sets in a similar way that we treat software. Someone's going to go through the effort of packaging that data and taking it from these standard archival file formats like NetCDF and turning it into something which is cloud native, a cloud optimized format that can be used through Object Store in these kind of environments. And so you did a presentation on that. I saw a few different people, because I looked at some of the names, people playing around with it. I'm getting the sense, though, that's still a work in progress, right? You know what it is, but you don't have it set up. So I want to just talk about it briefly and then give you another option. So if you are interested in these analysis-ready, cloud-optimized data sets, and again, this is all Ryan Abernathy's sort of work and group people he's worked with, you can go to PangeoForge, the catalog, or the catalog.pangeo.io to find references to data sets which have already been pushed up there. So just on the theme of precipitation, one of those data sets would be the Global Precipitation Climatology Project. So that's a 1 degree resolution, daily, 25-year observation data set from both satellites and gauge sensors on how much rain we got. And to get that data, it's as easy as pointing to somewhere in the cloud, a URL, a URI, and we get the data. I want you to get a sense of this data. This data is only 1 degree, 180 by 360, but it's got 9,000 time steps. It's 25 years of daily data. It's a good sized data set. And with that data set, what I can do is I can visualize it, I can play with it without having to download it locally. And if I wanted to see the weather doing whatever the weather does, so we're looking at time going forward, here's every week, here's the weather going along, and it's just scrolling through, grabbing frame by frame of this data. And this is just rainfall. Well, rainfall and snowfall, but it's the weather on our planet going through. And you can see the equator, but you don't see any other structure. And again, not a surprise for this group, but we may want to do something with this data, say like produce a climatology. Take those 9,000 different snapshots of precipitation and average them all together to find out what the average precipitation is, a long-term climatology. So again, the variable of interest here is precipitation. The way it's viewed is it's 9,000 different snapshots of 1 degree resolution data. Internally, it's stored as 447 different chunks. What's a chunk? Basically, it's grouped into 200 time units and then 180 by 360 spatial units as one blob of data. This blob of data is what's stored in the cloud system. So this data set is actually split up among 47 different key value pairs, each one which can be accessed independently. And so what you can do is then you can do a bit of analysis on it. It turns out this data set has some flags, precipitation values, which are very large or very small, are unavailable data. I can average all that data together. This is the X-array sort of workflow. And it's relatively quick to make that happen because I haven't actually done the calculation. You've probably heard of lazy calculations. It's just saying the data when it's done. When you average in time 9,000 different time snaps, you're going to get this data set, which will be 360 by 180. To actually force the calculation to occur, what I have to do is go through a load or a compute. And so you're seeing that what I'm doing is reducing down this roughly 2 gigabytes of data into a single file. It takes around 5 seconds. And then I can plot it. And when you plot it, remember, this is just precipitation data. You immediately see going, of course, yeah, well, there are the rainforests, right? We talk about the rainforests. We know there's rainforests in the northern part of South America, all the way through here in these islands. I was pointing this out to my daughter. I'm like, do you know about like the British Columbia rainforests? She's like, yeah. Well, where are they on the map? And of course, there we go. There's BC. There's the rainforests, right? Coming out of that data. So we can do these kind of things once the data is analysis ready and cloud optimized. Okay, that's all well and good for this data, which has already been pushed to the cloud, which is already in the Panjo Forge. What do you do about your data? Your data, which isn't really, maybe the world doesn't want it, we just want it. What do we do? So there are some alternatives. I'd like to highlight a relatively newer library to the ecosystem, something called Kerchunk. Kerchunk is a library that sits within the FSpec ecosystem. It's developed by the same set of developers. And the idea here is what Kerchunk is going to do is take a bunch of netcdf files, which are sitting out in the cloud, accessible by HTTP, or by Google Cloud Storage, and aggregate them together so that they are treated like a virtual data set. So it's czar-like, without actually having to make a complete copy of the data. So this is useful because you've got a lot of archival data already published out there, lots of netcdf files that are great for archiving, not so great for cloud analysis. And what Kerchunk is going to do is go through and index all of these files so that you can treat the data as if it was stored in czar. And in fact, just this morning, I opened up my phone and I noticed that there was a brand new Medium article published just yesterday. They had a Google Summer of Code student working on Kerchunk. So there's a reference if you want to follow up what the latest and greatest is of this library. But let me just show it to you in terms of what it can do. So the idea here of Kerchunk is once and only once, you pre-index all of those netcdf files and you create out of them a bunch of references into them. So what this code does is it generically takes some file which is sitting on cloud storage, GCS open. I'm opening that file, and then I'm going to index that file. That's what Kerchunk does. And it produces for me some output about what it is. So I'm going to run this code. And so it is taking that file and indexing it. I have a feeling what's going on. It takes more like 2 seconds, not 2 milliseconds. That's only because I had done it earlier, but that's fine. What this file is an index into that netcdf file. Remember, these netcdf files are about a gigabyte a piece. They're pretty massive. This file is a JSON file, a fairly light sidecar file, which acts as a reference or an index into it. So the idea here is this is the object which lives in cloud storage, and these are the references, and they're basically all of the chunks, all of the pieces that make up that netcdf5 folder, and these are the byte address offsets to each one of these variables. So what the effect of Kerchunk is to take a data set, which itself is netcdf, not convert it to ZAR, but index it so that the ZAR library can read that file as if it was already ZARified, because it knows exactly the byte locations and offsets to go into object storage to get that data out. So if you can do that for one file, you can do it for all of the files. And so again, this is stuff I just did on the weekend. You can take that. You can open the file, which is, I guess, not too surprising. I'm gonna jump down here to the next step. I can go through and I can loop through all of those files in cloud storage, and I can compute this index to them for each one, and then combine them all together with a function called multi-ZAR into a single JSON, which is the index to the entire data set. So what I've done is I did this earlier. It took about 35 minutes to index this 4 terabyte data set, and I put it into the shared library. So you've all got access to it. Now, it's in shared, it will persist. So there it is, that JSON file. Now, it's a good sized JSON file, right? It's a 400 meg index file, but it's representing 4 terabytes of data. It's all of the addresses for all of the variables in all of those files, all indexed. So one thing you could do if you didn't want to convert your data to ZAR is you could put your data up in cloud Google storage and then create these sidecar files that let other people access that data as if it was ZAR. Now, this file will persist because it's in our shared folder. What will not persist is the underlying cloud storage that I put onto that Scratch bucket. That will disappear in about 4 or 5 days. So we'll have to talk about if this is a solution you want or how you want to go about doing it, but that's the idea. Once you have this sidecar file, then what you can do is you can open up that 4 terabyte data set, all 4,800 time steps, okay, just shy of that, into one large, oh wait, I'm missing something really important. I better run that. I better run that one. I'm getting the wrong file to open up. I'm lazily opening up and constructing a virtual data set that represents it all. And what's going on is it's using FSpec's reference file system and then passing that to ZAR so that ZAR is looking at that file system, pretending that it is something like that. And so in about 16 seconds, which is still a lot faster, which is about the same time as downloading one file, I've opened up this 4,000 by 48 by 40 by 576 size data set, right? This is an enormous amount of data, but I'm able to treat this whole thing as one large blob. So what I can do is I can, again, lazily, I can now think of that entire data set and I could do something like scroll through it, right? So here is precipitation at any height level and at any time being shown up. And what's going on here is, let's just go through time. Let's go to another time. Every time I make a request, there's at 133 days, at 279 days, 69 days. Oh, there we go. What it's doing is it's going into this structure and only pulling out the objects or the specific parts of the data required to make this picture. I'm referencing a large data set and only grabbing what I need. Now, let's go back to some of the things we want to do with this data. Looking through the papers, I noticed that precipitation, we typically want to vertically integrate that. Okay, we can do that. We can do a vertical integral or a sum of some kind of that data. So what this will do is take all those layers and collapse them vertically. And again, this is a lazy operation. It takes more time than just this to actually take all that data and push it together, but I'm collapsing the vertical. So now this is the data. Now in memory, it's 14 gigs of data broken up into many thousands of tiny little chunks. So we can do this kind of operation, and we could visualize this and run it all the way through. So that's what this image is. This is just a visualization of the vertically integrated or vertically summed precipitation all the way through. And if I want to do something like compute a climatology on this data, I could do that. Now, it is faster than downloading. It's still not lightning fast, okay? So to do something like produce a climatology for just say 10 days, 80 of these frames. It's taken about 30 seconds. I could let it go for about 35 minutes and do the whole thing, but I wanted a demo that worked relatively quickly for our purposes. And you can see that when we get out of it, when we've run that, is I can see the climatology, the average. And again, this data set's on a water world, so we're looking at atmospheric precipitation, and you can see this sort of, I guess, intratropical convergence zone thing going on, but it's only over 10 days. What we really want is we want to be able to average it over the entire data set. We could let this run for the full amount of time, wait about 35 minutes, and you get the answer. Alternatively, you could just take this data, since we've already now chunked it, and you can do the conversion into ZAR, right? So I did this. Rather than doing this once, I want to play with it. Again, this was just what I was doing over the weekend. I ran this line to sort of chunk it up a little bit differently, and then just pump this stuff into ZAR, into my Scratch, so that anybody could access it. So what we can do is we can use ZAR, and of course you can do this too. You can go to that path. Everybody within M2LINES is able to see this. And very quickly, again, we're lazily loading it. We have that vertically integrated precipitation data. Okay, so it's still a good size of chunk. And then once I've got that data, I can visualize it. And the visualization is now pretty fast because I'm just going and now using ZAR itself to look at the weather inside my planet, right? So I can come along and I can see these systems, these weather systems propagating along. Maybe I can do something like come up with a climatology, okay? So again, running this in real time on this server. And this is the only reason why I wanted to use machines, because behind the scenes, it's kicking off about 16 threads. So I can get this reduction to happen in 30 seconds as opposed to 2 or 3 minutes, because that's how I timed this all out. So it's going to reduce this data down. Compute is actually forcing the computation to occur right now. The alternative is to use load, where you set up the calculation and then say replace that lazy array with its calculated version. And then once you've done that, we can make a plot, say, of the actual rendered data. So there is the climatology of this high resolution precipitation model. We see that there is this intertropical convergence zone, which I'm talking atmospheric scientists here. You're like, of course, James, but I was like, oh, cool. That we can see this all the way through. And I can see that in the sort of the subtropics, we've got these other 2 bands. Well, maybe I want to take that data and then zonally average as well. So I might take some zonal average of that and I get that characteristic plot. And this might be something that you want to train on, right? This is the high resolution model. You're going to create some lower resolution versions. And then of course you want to compare, does my numerical subgrid parameterization allow me to recover this structure? Or at least that's what I learned by reading one of Yanni and Paul's papers. So other things that we can do is we can do some coarsening of the data, right? I can take in that data set and I could say do a 16 times reduction of the data set, because coarsening, of course, is one of those operations we want to do. And we take a look at the difference between sort of the raw version and a coarsened version. And again, here I'm leveraging this data set. I've just put it into Scratch cloud storage. It's not going to persist there forever, but it's going to persist there for a few days. Maybe you're doing some intermediate processing. You want somewhere to put it for a while, but you don't want to keep it forever. If you do want to keep something forever, we should just spin up a different bucket and talk amongst as a community where you want to put it. But you can do these kind of coarsening operations very verbosely inside of a Jupyter Notebook environment. And hopefully what we're going to see here is the original data and then the coarsened sort of structure of it all. And of course, we can just go through time and take a look at how the original and the coarsened version work. Here's my story. Using Jupyter Hubs and Jupyter Notebooks allows you to produce a way of doing literate programming, like I saw with the L-squared notebook, that can be easily communicated with other people within your team and then outside. The expressiveness of using Xarray and the libraries that are around it mean that operations like coarsening become a single line, which traditionally might have been a bit more windy, say in a MATLAB type environment where you've got loops or you've got to handle each variable by itself. All of the low-level NetCDF stuff, the actual creating of the NetCDF library, totally abstracted away. Xarray and its backends are handling all of that. One of the values of treating your data sets as data sets is you'll notice that other than this one URL, I now don't need to talk about file names, right? I don't need any of that code, which is loop from first file to last file, time step 1, time step 2, time step 3. You're able to do these operations at a higher level. Running these things in the cloud, where your data is hosted in a cloud object store and your computation is next to it, facilitates this. So in terms of continuing on and sort of next steps, in terms of a conversation, if it's infrastructure related, okay, I guess I should just add that to my notes here. If it's actually an infrastructure thing, something's not working, there is no problem reaching out to us at 2i2co.org to sort. Oh, that's not what I wanted, or that. Yeah. Come on, double click. Come on, where is it? I want this. And of course, now my computer's just going slow. I'm on the last slide, so we should be okay. If it's an infrastructure question, send us a flag. If it's something that we can fix, we're happy to do it. If it's something that's more of a community issue, we might push it back, or it might be a package issue. You're trying to learn how to use Kerchunk. My suggestion is join one of the discourses out there. The one that I think has the most activity today is the Pangeo discourse. It's possible that another discourse one day will take it over. You obviously could use your own discussion forum within your own group, but the advantage of pairing up with a group like this is you're going to get a whole bunch of people who know about how these packages are interacting. I'm also trying to pay attention to it, to get a sense of what the community is doing as they do these Pangeo-like workflows. GitHub issues is good for like a specific package, but discourses are great for showing you how the tools work together. And I finally want to leave it off with this bit of an open-ended question. And I realize I'm at the end of my time here, so it's okay if we don't have time to go into this. But I really am interested to hear back from this community about what your pain points are, right? What could be better? How could the infrastructure that 2i2c is delivering make your research more impactful, accessible, and delightful? And again, I'm James Monroe, and if you need to reach out to me or want to continue this conversation anytime, this is how to get a hold of me in terms of an email address. Thank you for handling the technical issues at Expose, the reality of doing live, unpre-recorded demos, but thank you very much. So any follow-up or questions from the group, and I'm totally okay if you're like, oh, it's been 2 hours, I got to run to another meeting. That's totally cool.
Yeah, James, you had a high watermark much longer than a lot of people have just started jumping off, because I think we hit the next the hour. Yeah. But this was great, by the way. Thank you very much for doing this for us.
Okay, no, I'm glad. So my hope is, because I think if I remember right, this hub got spun up in about May as a piece of infrastructure, and I was trying to look in the logs, going, well, how much usage has it had since May? And there hasn't been much. So there's a little bit of, and I know there's lots of people in this community, and you're doing your machine learning. I would assume a lot of people are using laptops and desktops, maybe some HPC, but you're doing a lot of workflows on local infrastructure. These are more CPU cycles that are just sitting there. It's going to change. That's wonderful. That's wonderful, because we want to sort of leverage that infrastructure, because we do think it can enable things that you haven't been able to do before. If it's not working, and either technically, like you saw, it wasn't working for me today, reach out. But if it's not working from a training, community, knowledge, it's just not working, let me know and let me work with you to try and solve this. Because it's not just this community, but there's several of the Pangeo-like communities. This is all bleeding edge stuff, but it's transforming the way we're working.
No, I agree. We needed this tutorial to get us back on into starting to use it. As Drew says, we'll start using it now. Now that we know how to do it.
Sounds good.
Yeah. So thanks again for your time.
Okay, fantastic. I said, and at any time where there's I don't know if you do community meetings or annual workshops, but if you ever do one of those ones and there's space, I would be more than happy to be a fly on the wall. If nothing else, just to get to know you all a bit better, because this is the sort of the branch of science that I was moving away from as I transitioned to this 2I2C role. But
All right.
that'd be cool. Okay, thanks everybody. Have a great day. I'll turn off the recording now and it'll get posted for those who missed it.